In this videocast, we'll look at three different things. First of all, we'll look at factors that affect acid strength and why acids are strong or weak. And then we'll look at structurally 4 different kinds of acids and what makes them either strong or weak acids, or acids or not at all. And then lastly, we'll look at one other definition of acids and bases. First of all, factors that affect acid strength. Number 1 is polarity. Polarity means that there's a difference in electronegativity between two atoms. And between the hydrogen and its anion, there has to be a polarity difference going in this direction, meaning that X, the anion, must be more electronegative than hydrogen. Must be more electronegative than hydrogen. Now, if you forgot the trend of electronegativity on the periodic table, it's really important for you to know this today. So take a look at the periodic table. I'll try to get it onto the screen here. Take a look at the entire periodic table. And electronegativity increases up and to the right, meaning that fluorine is the most electronegative atom on the periodic table. And then electronegativity increases down, and it decreases as you go down and decreases as you go to the left. So keeping that in mind all the time when we're talking today about polarity, knowing that the most electronegative thing is up here, and a difference in electronegativity between two atoms causes something to have a polarized bond. So, factor number 1 that causes electronegativity is that causes acidity, is that there must be a polarized bond between the hydrogen and its anion. And it must be in that direction. The more positive thing over here, the more negative thing over here. Second thing is the bond strength between hydrogen and the anion. It has to be strong, but not too strong. And this is very evident, strong but not too strong, if you just look at the halogen acids. HF is a weak acid, HCl is a strong acid, HBr is a stronger acid, and HI is an extremely strong acid. And so this bond between H and F is too strong because the electronegativity difference between H and F are too great. HCl becomes a strong acid now because the bond between H and Cl is strong but not too strong. And HBr, the bond becomes a little bit weaker, but it's strong enough, and same thing with HI. Last factor that affects acid strength is the stability of the conjugate base. Stability of conjugate base. The conjugate base, remember, is what's left over after the acid has released its proton. So after the H is cleaved off of the acid, the H plus has been donated, what's left over? The X minus thing. And the stability of that determines how strong an acid is going to be. If it's very stable, the acid can be stronger. And we'll show you a couple of ways that can make that conjugate base more stable. Next, let's look at 4 different kinds of acid and what factors from above make these acids be strong or weak. The first ones we'll look at are binary acids. Binary acids are H and something else, some anion that's attached to it. Acids that you might know would be like H2S, HBr, HCl. Those are binary acids because they have 2 different kinds of elements in them. One is hydrogen, the other one is some type of anion. Well, the primary thing that makes a binary acid strong or not strong is bond strength from above. Remember, in bond strength, it must be strong, but not too strong. Strong, but not too strong. Okay? So for the example that I used above is that in the halogen acids, the bond is too strong here in HF, so it's a weak acid, but the bond is just right in strength here for HCl, HBr, and HI to make it be a strong acid. The bond in H2S is actually a little bit too weak, and because sulfur is a little not quite electronegative enough, and so it's not a strong acid. So bond strength is the governing thing for binary acids, whether it becomes strong or not strong. It's going to be strong, but not too strong. Second are oxyacids. Those are acids that contain oxygen. They've got some nonmetal in them, an oxygen attached to it, a hydrogen attached to that. This hydrogen is the acidic hydrogen that can be cleaved off or given away. This nonmetal right here may have one or more oxygens attached to it. It must have polarization in this direction to make it strong. And the more polarized this area of the molecule is, the stronger the acid. And so polarization from up above right here is the factor that mostly affects oxyacids in terms of strength. Oxyacids that might be familiar to you might be something like HClO or HClO2 or HClO3 or HClO4. As you know, as you add more oxygens here, they become stronger acids. Why is that? Because the polarized area around the Cl is stronger because of the presence of more oxygens. A lot of people, when they see these formulas written as such, HClO, HClO2, HClO3, draw the Lewis dot structures incorrectly. Take a look at this method of drawing it. This is the correct way to have it, where you have an OH linkage attached to the central atom. All of these acids, when you draw the Lewis electron dot structure of them, should have the chlorine atom and then an O and an H attached to it. If it's HClO, it really should be ClOH or HOCl written. If it has 2 oxygens or 3 or 4, it just means it has an extra oxygen attached to the central atom. And this actually is the Lewis electron dot structure for HClO4. And it's extremely strong acid because this area of the molecule right here is highly polarized. And it's very polar, or it has a strong dipole moment in this direction, where it's very negative over here due to the presence of lots of electronegative oxygens, and very positive over here, and so it's real easy to cleave off that oxygen, making it a strong acid. If these oxygens were not present, like it was just ClOH right here, we'd say that it's a weak acid because it's not polarized as much. These oxygens aren't present to make it quite as electronegative over here. But this hydrogen can be given away to a limited extent because it is a weak acid. So oxyacids are affected by the polarity. Be careful of these now. Remember, you can replace Cl with Br, and you can have HBrO, HBrO2, HBrO3, and they're written the same way with the Br here. Or you could replace it with I, and you could put I in here as well. And those will make the same type of oxyacids. Be careful of how you draw the Lewis dot structures on those, making sure that you have the OH being the active part of the acid. The next type of acid are called carboxylic acids, and these always take on the format of some carbon atom double bonded to an oxygen, single bonded to an OH. This carbon atom might also be connected to other carbons or carbon-hydrogen connections, such as this one, CH3COOH, which you might know as acetic acid. There could be more carbons attached to this as well, and it could be a longer chain. The thing that makes a carboxylic acid strong is the third factor up above here, the stability of its conjugate base. The stability of its conjugate base, remember, occurs after it's released its proton. So after this hydrogen is gone, what makes this area of the molecule more stable? Well, you guys that are good Lewis electron dot structure drawers are jumping up and down right now, because you can see that it could also form a double bond with this oxygen and a single bond with this oxygen. And as a matter of fact, it swaps between these two states, where the double bond is here some of the time and here some of the time. And when you actually go in and measure the strength of those bonds, it turns out that there's like a bond and a half there. We gave this bond and a half or sharing of the double bond a special name. We call this resonance. And when the double bond resonates, it causes much more stability in the conjugate base. And that makes carboxylic acids be stronger. And they're not necessarily like hyperhickel high, honohickel OH2SO4 that we learned, but the better the stability that it has, the stronger the base will be. Last classification is a special group called amino acids. And amino acids are the building blocks of proteins inside of living things. And amino acids are actually acids, but also have what's called an amino group in them, which is basic. So they're actually base acids. Oh, they're acid bases. Which are they? Well, as a matter of fact, they're both. And they always take on this format. There is the amine group with a nitrogen connected to two hydrogens and an unshared pair of electrons attached to a carbon and then attached to a carboxylic acid group. And this carbon right here can be attached to one or more carbons. It could just be a hydrogen right here, or I'm going to put an R here, meaning that it is theoretically possible to have a long chain of carbons. If it was just a hydrogen right here, it would be the amino acid called glycine. If it was a CH3 group attached here, it would be the amino acid called alanine, in case you're familiar with any amino acids from biology class. Anyway, the thing that makes this acidic and also basic is this hydrogen right out here from the carboxylic acid area of the molecule. And as a matter of fact, you might notice that these amino acids could actually react with themselves. The hydrogen could be cleaved off and shared with this nitrogen right here. And then we could end up having the unshared pair of electrons right here and the resonance between this double bond right here. That actually happens. When they swap hydrogens with themselves, they form a special ion called a ZWITTERION, a zwitterion. And it's actually quite possible that they do this very often because they become very stable in this zwitterion form and take on some properties like ionic compounds. To read more about this, take a look at the Chemistry and Life box on page 707 in your textbook. Page 707 if you want to read more about amino acids. So let's do a couple of problems using those things that you've learned about acid strength. Arrange the compounds in each of the following series in order of increasing acid strength. The first one is ASH3, HI, NHI, and H2O. I think it's easiest to take the ones that jump out at you right away, and HI does to me because that's a strong acid. And so I'd list that way over here on the list as the strongest acid right away. Moving along down from there and taking a look at these, the one that jumps out at me next is the NaH. Because remember, one of the primary things that makes something acidic is that it must have a electronegativity in this direction going towards the anion. And if you look at this, it doesn't even have an anion. The anion is the H. The H must be attracted or connected to something that is more electronegative than it. And as a matter of fact, NaH, not that way. That way because sodium is less electronegative than hydrogen. So in my list, I'd put NaH as being the very least acidic. As a matter of fact, it's actually quite basic. The next two then are a toss-up, H2O and ASH3. And if you look on the periodic table, you can find out that arsenic and oxygen are actually near each other on the periodic table, but not right next to each other. If I can zoom this out just a little bit, here is oxygen on the periodic table right up here, and here's arsenic right down here. Who's more electronegative? Well, obviously the oxygen would be because it's really close to fluorine, right? And remember, one of the things that makes something be an acid is that there is a connection between the hydrogen ion and the anion that has polarity going in this direction. And the stronger the bond, or the more electronegativity difference, as long as it's not too strong, makes it be more acidic. So if you look at these two, ASH3 is less electronegative than water. So I'd have to say that water would actually be my next most acidic thing. And ASH3 would probably be maybe even slightly basic. So there's my order for letter A. Letter B, it now says, in order of increasing acidic strength, I've got H2SeO3, H2SeO4, and H2O. Now, if you look at just between the two Se-containing molecules, the Se-containing molecules, the one with more oxygens is going to be more acidic. So I'd say H2SeO4 is definitely going to be stronger than H2SeO3. As a matter of fact, that's true because this has a more electronegative oxygen, one more electronegative oxygen around the Se than the SeO3 does. And these actually can donate protons to water, which makes water my least acidic item compared to these Se-containing oxygens. Last page of notes. What makes an oxygen-containing acid have stronger acid-like properties? Well, remember there's one really important property for oxygen-containing acids, and that is around the central atom. Remember, it always takes on this form. How many oxygens are bonded around it? The more oxygens you have, the more acidic the thing is. And all you have to do is take a look at your HClO, HClO2, HClO3, and HClO4. You know that acid strength increases as we go down here because we have more oxygens around the central atom. Therefore, it's more electronegative in this area, and it sets up more of a dipole moment. Next question, what is a carboxylic acid? What part of the structure makes it acidic? Draw it here, draw it now. Well, a carboxylic acid, remember, has a C, double bond O, OH. And this C is connected to something else. Sometimes another carbon, sometimes just an oxygen. Sometimes just a hydrogen, as long as it ends up with 4 bonds. It could also be another C here. But the thing that makes a carboxylic acid an acid is that it has this hydrogen right here that can be donated or cleaved off. And remember, when it does that, the double bond can be shared between these two, and therefore it gives it stability for the conjugate base, because you can share this double bond between the two of them, and we get what's called resonance. All right, last concept in the chapter is that generally we use the Bronsted-Lowry definitions of acids and bases, but sometimes that's not broad enough. Here is one other way of looking at acidic and basic things. This is called the Lewis definition of acids and bases. And in the Lewis definition of acids and bases, we say, or we redefine acids not in terms of proton donors and proton acceptors anymore, but in terms of electrons. Remembering electrons have a negative charge, we say that Lewis acids are electron pair acceptors. And we say that bases are electron pair donors. They give away electrons. So it's kind of opposite of what the Bronsted-Lowry definition was. Remember, acids were proton donors? Well, here, acids are electron acceptors. And the reason that they're opposite of each other is because, of course, hydrogen ions, or protons, are positive, and electrons are negative. So, in terms of Lewis, we say that they're electron acceptors, and we say that bases are electron pair donors. And everything we've looked at in terms of Lewis bases already have had some unshared pairs of electrons that can be donated, or at least thought of as being donated. If you remember For example, water we lots of times used as an example of something that could accept a hydrogen. And when it does that, what happens? Well, the water in effect donates the electrons to the hydrogen. So everything that is a base in the Bronsted-Lowry sense, a proton acceptor, is also a base in the Lewis sense as being an electron pair donor. In the Lewis theory, however, a base can donate its electron pair to something other than H+. The Lewis definition therefore greatly increases the number of species that can be considered acids. Here's an example reaction. Let's pretend that we had the base NH3. We've seen this act as a base before and be a good acceptor of protons. But let's pretend it encounters something that doesn't have protons, like for instance BF3. Well, BF3 is electron deficient around the boron, and it would be a good acceptor of electrons to complete the octet and therefore bond real nicely with the NH3. We can define it now and say that NH3 is acting as a base because it's donating electrons to BF3, and BF3 is an acid because it's accepting the electrons from NH3. And if we completed this reaction and drew the arrows for it, we'd end up with NH3 BF3 bonded together. This would be a Lewis acid-base reaction. What feature must any molecule or ion have to act as a Lewis base? Well, it's got to have that unshared pair of electrons, and we see that commonly on nitrogens and lots of times on oxygens, like in water or in ammonia. That's why they can act as Lewis bases, just like they can act as regular Bronsted-Lowry bases. So here is really why metal ions dissolved in water act acidic, is because of the Lewis definition. Well, if you look at a metal such as like Fe+2, the +2 charge means that it has lost 2 electrons, and so it's electron deficient. And so when it encounters something like water, when it's dissolved in water, it's a good acceptor of these electrons. And when it's an electron acceptor, remember, it acts acting acidic. Chromium is a good example of this, and so is zinc. And they are surrounded or hydrated by water molecules, causing them to act as Lewis acids. A good example of this is Fe+3. Fe+3, we write it like that and then just put a little AQ down here, meaning that it's dissolved in water. But technically, you can write it as this: FeH2O6 with a +3 charge, because there are really 6 water molecules that have surrounded the Fe+3 ion and kind of connected with it. We don't write it like this very often because it's more time consuming, and we are just usually concerned about the species that's really going to do something. But in terms of Lewis acids and bases, it's nice to write it like this, because then you can illustrate how this could, in a Bronsted-Lowry sense, also act as an acid, as FeH2O5OH with a +2 charge and give away a proton. So if we took this and said, okay, go ahead and act like a Bronsted-Lowry base, here we could have it with an OH like this, and it would act as a Bronsted-Lowry acid because it would technically be giving away a hydrogen. I think I said base before, I meant as an acid. So let's take a look at generally hydrolysis reactions with increasing charge and decreasing radius of the ion. In other words, things become more acidic as the charge gets bigger and as the radius decreases. List the following in cations in order of acidity. Well, the one that's going to be the smallest and with the biggest charge is going to be Fe+3. They get smaller as they lose electrons, remember, because they keep the same number of protons. And this also has the greatest charge. So this would be my most acidic. My second most acidic would be Fe+2 because it has a smaller radius than does calcium. Calcium and iron happen to be in the same period on the periodic table, and remember, atomic radius decreases as you go to the right because you get more protons in the nucleus. And my least acidic would be Ca+2. So you can see that in terms of Lewis acids and bases, metal ions can act as acids because they're good acceptors of electrons, usually from water. And we can also more broadly define Lewis bases as things that have unshared pairs of electrons that can go ahead and donate.